Hello, Chemistry 10HH students. This is Mrs. Altman. We are on video number 38, Gases, Part 4. Here are our objectives for today's video. Pause here. So when we're doing chemical reactions that involve gases, you will sometimes need to be able to use the volume of the gas in order to do the stoichiometry calculations. In order to do so, if you are at STP, you may use the relationship that 1 mole is equal to 22.42 liters, which I'm going to show you where that derives from, because if you're not at STP, you will need to derive it yourself. So molar volume is just the volume of 1 mole of a gas. So what you would do is you would plug in 1 for the number of moles. R is the same. At STP, it's 273.15, and the pressure is 1 atm. Which if you put this in a calculator, you actually get 22.41 if you derive it this way, but 22.42 is the accepted value. But if you are not at STP, then you will need to derive the value, and whatever you get is what you use instead of 22.42. Pause here. Right, so this one is pretty straightforward, just doing a little unit conversion here. The 22.42 does not impact sig fig, so I'm going to round to 3 significant figures. So 2.02 moles. Pause here. So everything we learned in chapter 3 about stoichiometry still applies here. So it's just a stoichiometry calculation, which we're starting with 312 grams of calcium carbonate. Meaning, going back to my chapter 3, I need to convert this to moles first. And I'm going to need molar mass for that. When I go to the balanced chemical equation, I see that there's 1 mole of CO2 produced for every 1 mole of calcium carbonate. And then the part that is new, since this is at STP, I can assume that it is 22.42 liters of CO2 for every 1 mole of CO2. Put this in my calculator, round to 3 significant figures, and I got 69.9 liters. Pause here. So sometimes we'll want to determine the density of a gas, and you're not always going to need this equation to do so. So if you just happen to know the mass and the volume, you can just divide mass by volume. That's totally fine. For density of a gas, we're typically going to do grams per liter instead of grams per milliliter. The reason being that gases tend to be very, very low in density. And so you're going to just end up with negative orders of magnitude if you do it in grams per milliliter. So it's just more practical to do it in grams per liter. And this equation here only works if density is in grams per liter. Let's take a look at an example of applying this equation. Pause here. I'm just going to start by listing everything that is in the question. So I have everything I need. You'll sometimes see me abbreviate molar mass to MW, which really is for molar weight. There's this historical reason why you see that. Feel free to do the same. Plug this all in, I'm going to round to 3 significant figures. So I got 28.1 grams per mole. And then the question goes on to say, if this gas is diatomic, what is its identity? So 28.1 divided by 2 is approximately 14.05, but that Nearest makes no difference. I go to my periodic table, I find what has a mass of 14, and it is nitrogen, so this gas is N2. I had to tell you in the problem that the gas was diatomic, otherwise there wouldn't be any way for you to know. If it wasn't diatomic, you would get silicon, but that would be a bad question because silicon is not a gas. So typically, if I'm going to ask you for the identity of a gas, it's going to be something that matches up to something that is known to be a gas, meaning one of the Hunkelbrefs or a noble gas. Great, that is all for tonight's video. Thank you so much for watching and have a great night.